Hi everybody, Mr. Johnston here, and today we're going to talk about the types of bonds. We'll kind of review some of the things that we talked about in class, as well as we'll get into some more details about ionic bonding. So first, the three main types of bonds, as we mentioned: ionic bonds, covalent bonds, and metallic bonds. And so really, the type of bond that forms between the elements is dependent on their electronegativity values. So looking back to the periodic table and remembering that trend in electronegativity, as we go across a group, the electronegativity values increase. As we go down as we go down a group, the electronegativity values decrease. So the electronegativity values get greatest when we have the element fluorine. That's the most electronegative. Also, you'll notice that the noble gases, they do not have electronegativity values because noble gases do not form chemical bonds. So an ionic bond, real quick, is the elements that create an ionic bond have a large difference in their electronegativity values. So you can think of an ionic bond is typically formed when a metal has a really low electronegativity and a non-metal, which has typically a high electronegativity. When they form a bond, it's an ionic bond. And this is going to result in the transfer of electrons. So the thing with higher electronegativity in this diagram is chlorine. It actually has such a high electronegativity that it takes the electron from the sodium atom, which sodium has a low electronegativity, and results in ions. So the sodium ends up being a positive ion and the chlorine ends up being a negative ion. And those opposite charges, the positive and the negative, that's what attracts the atoms together and holds them together as a bond. A covalent bond, the elements in a covalent bond have similar electronegativities, and those are relatively high electronegativities. A covalent bond forms between two atoms that are non-metal, so they both have higher electronegativities. And we always think of a covalent bond as sharing electrons. It is worth noting that the sharing of electrons is not always equal, and the result of unequal sharing of electrons is a polar covalent bond. And so if we take a look, if two things share electrons relatively equally, we refer to that as nonpolar covalent. And if they don't share equally, we think of that as polar covalent. One atom pulls the electrons more than the other atom. And so what we end up with is this shared pair of electrons gets pulled towards one atom and away from another atom. Even though they're still sharing, we end up with we refer to as partial negative and partial positive charges. It is worth noting that the whole thing with bond types can really be thought of as a spectrum, and it all boils down to this difference in electronegativity values. So if we look at the electronegativity value difference, then we can see what type of bond it is. If that difference in electronegativity values is relatively small, then it's going to be nonpolar covalent. If we have a really big difference in electronegativity values, then that's an ionic bond. And if it's kind of that intermediate, somewhat different, then that's polar covalent. And our third type of bond is a metallic bond. A metallic bond is when both atoms have similar and relatively low electronegativities. And usually, as the name would imply, a metallic bond forms between metal atoms. Metal atoms have low electronegativities. When those metal atoms bond together, each metal atom sort of donates one or more of its valence electrons to what we refer to as the sea of electrons. And the electrons in this sea of electrons can bounce around from one atom to another. They are not fixed to any one particular atom, but instead those atoms, or the electrons, are free to move around. And this is one of the things that gives metals their unique property, is that idea that the electrons can move about between atoms. The valence electrons, we should emphasize. So, a little more now about ionic bonds. Ionic bonds form, again, when atoms lose or gain electrons to achieve a stable electron configuration. So this example, we have a sodium atom. And again, a sodium atom is a neutral atom, and it has 11 electrons and 11 protons. Sodium has one valence electron, so I find that highest energy level, in this case the third energy level, and it's got one valence electron there. The sodium ion, on the other hand, has 10 electrons and 11 protons, and so it lost that one valence electron to achieve a stable noble gas configuration. So ions form when atoms lose electrons. Ions can also form when atoms gain electrons. And so this atom is chlorine. Chlorine, the neutral atom, has 17 electrons and 17 protons. The electron configuration has 7 valence electrons. Now, the chlorine ion has 18 electrons and 17 protons. And so it actually gained one electron in order to achieve a stable configuration. And a stable configuration is any time we complete an energy level. A stable configuration is always S2P6. We call that an octet. Going back to the periodic table, we can actually remember the elements in a group always have the same number of valence electrons. So the alkali metals, they all have one valence electron. The alkaline earth metals, they all have 2 valence electrons. The halogens, they all have 7 valence electrons. If we look at the noble gases, they all have 8 valence electrons. The exception, of course, is hydrogen, or helium has 2 valence electrons, but it's still stable. The other groups on the periodic table, we can predict how many valence electrons they have. And this is important because we can then also predict which ions they'll form. So if we want to talk about ion formation, the transition metals, the number of valence electrons on a transition metals really depends on the specific configuration. So it's a little harder just to, draw a whole thing for the one group when each one is a bit different. So the alkali metals, they're all going to lose that one valence electron to form positive 1 ions. The alkaline earth metals, they're going to lose 2 valence electrons to form positive 2 ions. The halogens are going to gain 1 valence electron to form negative 1 ions. The group 16, they gain 2 valence electrons to form negative 2 ions. Remember, the noble gases are stable. They don't form ions. The group 15 would form negative 3 ions. This group 13, aluminum on down, would form plus 3 ions because they got 3 valence electrons. They're going to lose those 3 valence electrons to form plus 3 ions. And the transition metals, the charge really depends on the specific number of valence electrons. And some transition metals can even form more than one type of cation. More on that when we get to naming. I do want to talk just a little bit about what we refer to as Lewis dot diagrams, or sometimes electron dot diagrams, and how we can use these to show ionic bonding. So, first, the valence electrons of an atom can be represented as dots around a symbol. And this is how this looks. We write the symbol of the element, and I always think of like a square around that symbol, because the edges of the square, the sides of the square, that's where the valence electrons go. And I always think of each side of the square as an orbital. So one side of the square represents like the s orbital, and the other sides represent like those 3 p orbitals. And so the maximum number of valence electrons that we can put around the symbol is 8. The first 2 electrons, remember, we always pair up in the s orbital. So we put 2 dots for the 2 electrons that might go in the s orbital. And then remember Hund's rule, electrons don't pair up until they have to. So I'm going to put 1 dot on each side, and then they start to pair up, and the electrons go together as they fill that energy sublevel. A couple more examples. Here's magnesium. Now, magnesium is an alkaline earth metal. It has 2 valence electrons. Those 2 valence electrons are in an s sublevel, so I put 2 dots next to magnesium to represent those 2 valence electrons. Here's nitrogen. Nitrogen has 2 electrons in an s sublevel and 3 electrons in a p sublevel. So its electron dot diagram, I would put 2 dots for the 2 electrons in the s sublevel, and then 1 dot on each side, because each electron in a p would be spread out, and 1 in each p orbital. So we can actually use the Lewis dot diagrams to show the transfer of electrons in an ionic bond. And I was going to go through a couple of examples on your reading guide. So why don't you pull out that reading guide, and we'll take a look at a couple of them together.